go into an embassy, you're going to get marriage papers, and afterwards you're
Okay, that's it. So, sorry for the delay. It's all INT's fault at first. The next talk will be by Chen. We'll talk about EP and EA facilities complementary to the US EIC from JLab 12 to low energy EIC.
Okay, yeah. Thank you for the invitation. I will tell you about the JLab 12, especially the solid program, and then probably more on the EIC in China. Oh. Okay. We all know the standard model works great. It's been tested in huge range. Everything seems working. All the search for new physics seems nothing new. And so people are going to dark sector or neutrinos. But there's a big thing, of course, the big elephant in the room is we still don't understand one major part of the standard model, which is the QCD, strong interaction when it's in confinement region. And we don't understand how confinement works. And study hadron structure is probably the best way to learn about this. So we all know, I will go through this quickly because most of you already know. There's a lot of puzzles. Proton mass, gluon should play a major role. Quarks is only less than 10 MeV, while nucleon is 1 GeV. Most of these should come from gluon dynamics. And we also all know the proton spin puzzles, which leads us, we need to study 3D structures, TMDs, GPDs. Okay. DIS has been a really powerful tool. We learned all the from structure function unpolarized, cover many others. We learned all the power distributions. And we know the valence quark distribution very well, and we know also Scie and the gluons, although at probably very low X. And very high X, we still have some unknown puzzles. And I want to point out the high X region is mostly the valence quark dominant. And then you go in low X, you slowly get into Scie, and then near the low X, it's all gluon dominant. So there are many facilities use EP or EA to study nucleon structures, hadron structures. And I will focus on the currently still running COMPASS and JLab. I'm not going to talk about COMPASS, just mention this. But the future, of course, is what the focus of this workshop is about EIC. And I'm not going to talk about anything about the hadron collisions. And I will say a little bit about what's going on in China for the complementary low energy EICs. So look at the X range. JLab is focused on is one. Just not see it very well. So the high X region, JLab 12 GeV was a very good job. And it's better. That's how it works. Yeah, the China EIC low energy version will cover the X range from a few times 10⁻³ all the way up. And of course, US version will go another order of magnitude. So I start with JLab, and we focus a little bit on the solid program. And the 12 GeV upgrade took about 5 years and finally completed last year. Although we already started the experiment before it's fully complete during the commissioning. And Rolf talked about some of the outcome, or reading a few papers published. We have 3 existing halls have some kind of upgrade and build a new halls. And however, we have actually mostly no upgrade other than the beamline. So we're looking for new future upgrade. The solid and the modular. Rolf also mentioned about this. So the science question we want to answer is, one is the proton mass, one is the spin, and especially the rule of orbital angular momentum. And we want to reveal the 3D structure through the GPDs and TMDs to learn about full structure of nucleon. And also with the opportunity by doing pair evaluation, we can learn about beyond the same model physics. So these are the three main programs we started the Solenoidal project. One is to study TMDs, which need a very high luminosities, and together with a large acceptance. So that's the key of solid is we have to handle high luminosity while acceptance is almost cover 2 pi plus the azimuthal angle from we can choose a large range. So by doing this, we can map out the 3D structure of TMDs and GPDs. And also, we can reach 10 to 39 luminosity to do a pair evaluation experiment to make a very unique contributions here. And we will be able to also do the threshold, very high precision threshold GSI productions to make contribution in proton mass studies. It's a very strong collaboration with over 300 collaborators from 72 institutions, 13 countries. We expect to have significant international contributions. This has been strongly endorsed in the long-range plan. Okay, I'll talk about this physics topics. One is the proton mass, one is the spin, and the 3D structures. I will not talk about the parity program. Proton mass been discussed last week, and tomorrow we have a more dedicated talk. So I will just go through this quickly. If you use any momentum tensor put into your wave function of the protons, you can decompose this into a term. I'll take the trace. You will take only the trace anomaly term and the explicit proton mass, quark mass term will remain. Quark mass term has small contributions, and people have done calculations through lattice or through color perturbation and come up. Instead of actually it's more than 1%, it's more close to around 10%. So the remaining part is come from QCD trace anomaly. This is a kind of more frame independent. You can also choose a rest frame. Then you can choose just the energy term. The rest frame of the proton, the energy term can be decomposed into 4 different terms. And because it's a rest frame, the energy is its mass. So these 4 terms are quark mass, quark energy, gluon energy, and the last term is the E field squared minus V field squared is the trace anomaly. So how to relate these to measurements? The other terms actually all can be quickly related to that. Only the last term, the trace anomaly, we don't fully understand how to measure this, although with some models, people already relate this to the heavy quark threshold productions. You probably heard of the talk last week. And people still, the early work 20 years ago already, within a model, you can relate that. But there are more work ongoing. There are 2 workshops happening in Zenity and others organize that. So you will hear a lot more tomorrow. So with solid, we can actually do the threshold GSI productions. can do it very well. In addition to that, we can also learn about the penny quark issue too. EIC will be able to do the epsilon predictions. So these two combined should help us learn a lot about this proton mass. Okay, the second topic I'm going to mention the physics is the spins. And there are many years, also almost 30 years experiment, but still we don't really cover as wide, as precise as unpolar situations. And there are puzzle of spin decompositions been discussed also in the last week or so. And this is one of the paper decomposition, and also GeV has a collaboration try to do the globe fit of that. So we understood to a certain level, but still there are quite a bit of unknown. In particular, the orbital momentum, we have very little knowledge of that. With EIC, we can learn through 3D structure, which we'll continue next. We'll learn about this, but also the spin, not only the total, but you also want to see how it decomposes into different flavors. And this is one of the C quark distributions. EIC will do a very nice job here. And most of people know very well, now we have these big distributions. If you integrate out, you can get to the TMDs and GPDs. They relate to the traditional 1D structures or form factors. So we can either do TMDs or GPDs to get the imaging. I will say a little bit more about the TMDs. With GeV 12 GeV, especially with the solid, we can do very high precisions, which requires high luminosity and large acceptance. That's what the solid can do. There are a number of experiments approved by GeV PAC with high rating, both with transverse longitudinal polarized helium-3 to study neutron, and also transverse polarized proton to study the protons. So, of course, combined with EIC, we can do the full mapping of these series functions. GeV will do a very good job in the HIAF region, and then EIC will cover the low X region, which can help do a 3D imaging in 3D momentum space. There's another quantity is transversal distributions. This is more valence-like distributions. So solid can do a really nice job. We improve by order of magnitude of the transversal distributions, and we'll be able to get the tensor charge to very tiny error bars, which is one of the fundamental quantities that already have very nice predictions. And there seems to have a little bit of attention for the U quark transversities, tensor charge.
So last week we discussed quite a bit about lattice.
Okay.
And lattice has made enormous progress.
Yes.
But the uncertainties which are shown at lattice are very often only the statistical one, and the systematics is completely missing. So I think if we show things like this, it should be pointed out that there are quite a bit of larger range of missing. And also, it's not obvious that transversity you have to measure really only at high X to get the tensor charge. There might be also important contributions from lower X.
First, lattice, as my understanding, transverse tensor charge is one of the quantities actually very.
That is correct, but there's still most of the uncertainties neglect systematics.
Yes, yeah. I am not trying to claim this contains all the systematics. That's the error they're showing. But this is one of the quantity much more stable. As they did 10 years ago, already they got the X-ray charge, which turned out to be moving around. There are a lot of noise, make it difficult. But tensor charge is, some of our lattice friends told us this is the best quantity we can test. So I think it's extremely important we measure this. Yes, there will be lots of contributions, how large, we still don't know. But it's the good thing with the transversity is it decoupled from gluons. So it's not divergent to out like that. I'm not claiming this necessarily small.
I'll come back during my talk. I have some
Sure,
results to show
yeah,
you.
yes.
And actually, I would not say that, certainly the numbers on the lattice side somewhat converge, but only for the isobacter component. Because, you know, there you get disconnected the contribution, so on. For the single flavor values that you are putting there, things are much more questionable. For example, the results you see there quoted Alexandre et al. With very narrow points, that they have only one lattice spacing. So they have no study of continuum extrapolation errors, no study of large volume extrapolation effects, etc., etc. So
you're absolutely right. The ISOs.
Exactly.
Yes.
I find it just dangerous to show such type of things and giving the impression everything is understood. I don't think, and as I said, there's enormous progress, and I don't want to in any way be negative on also progress, but I don't think also if we show this plots that it gives impressions that we have everything under control. I don't think we are there. Not even for transversity, which indeed the gluon doesn't mix in.
Now I agree with you that the lattice they should show more of the systematics, but unfortunately I cannot add system myself. Whatever they show, that's what I'm showing.
The important point you can make there is that the enormous relative increase in precision that you can get with solid, but I mean not more than this. This is already quite an important message.
Right.
What is this line at 0.6? Is that how far the data is extending?
Which one?
I mean,
These are the Mayer reading. Yes. Yeah.
So beyond that?
Below this, logs were not measuring.
About
this, actually the data is integrated over the last data point, integrated over to the range. The average, the last thing we have, average is around here. The coverage is go over, and of course we don't have all the way to EicC-1. You know that to go there, you have to go above the resonance rate.
To some extent, your smaller error bars are because you have fixed parameterization, right?
Partly, yes. It is within certain model that Alex can take this. It's try to say the improvement over the existing ones. They are outside this range. We did some study in this within different model. They tried to see how sensitive it is, but because it's outside, actually more it's logs, as they will point out.
In these pictures that we were showing at large X, we don't know U, we don't know D, and then all of a sudden we will know very well the transversity, which is well.
No, we didn't. It's when
you know what happens if your function decreases and becomes 0, and x equals 0, and it's 1. And what happens is that you see that the errors are shrinking. But we have to think it's relative error.
the integration to the sum.
To the error. So the ratio of the value to the error or relative error is incredibly big. It's not in this plot. Okay. So this is of course a very counterintuitive, but once you understand how it works,
But
and I believe you understand very well because you can multiple the size.
Hello, when you talk about HIAF, we don't know very well the D over U ratio. Both goes towards 0. If you talk about just U itself, the error cannot be huge.
And those are huge.
When you do the ratio, the error became large.
What is the W cut? What's this data which you put?
2.3.
W.
Yes.
Uh-huh.
Okay. I'll go on to EIC, but for the EIC, I will just pass through very quickly. Because everybody here, that's the focus of this workshop. We all know it's been started from 10 years ago, long-range plan already start point out it's the next frontier. And then the last long-range plan take this as the highest priority and have the white paper and this Academy of Science review report just came out last just a few months ago. So there are the ERICS and GeV version, and of course there's a range and just centered around there. And GeV is fixed target, and then future also the HIAF you will hear tomorrow. So the physics questions are the spin, 3Ds, proton mass, and ground saturation, and how the nuclear environment affects the PDF, how the interactions in there, and also the opportunity to study physics beyond sand models using Pareto variations. So I will focus on the China side. It's the EIC at HIAF. So HIAF is the high intensity heavy ion accelerator facility proposed and get approved to build. It's led by Institute of Modern Physics, Academy of Science in China. This is the latest design. It's finalized, so they start constructing now. So this facility is mainly try to do rare isotope beam for very low energy nuclear structure studies. So it's the site is chosen. That's this is China, just in this corner. It's in Guangdong province on the East Coast, southeast coast. It's near Macau and Hong Kong. And if you look at here, this is Taiwan. Here is Hong Kong. So it's also near the beach. This is a HIAF timeline. It's been proposed almost 10 years ago and get approved a few years earlier. And now the site civil construction already started. The machine construction will be starting now, actually this year. The money is coming down, it's fully approved. It's expect to be finished by 2022, and the commissioning operation will start a year later. So when near the end of the final approval, they will try to look at, can we do more? So that's the time it was proposed, maybe add an electron ring. You can do a low energy version of EIC. So the first version was proposed in 2013. It's a 3 GeV electrons with 12 GeV proton. And of course, it goes all the way, it's polarized, and ion can go all the way to uranium. So that's the first version was proposed. And at the same time, another version, also at 2013, there are many discussions. So that's another version, try to use figure 8 to preserve the spins. And it was...
Can I ask a question?
Yes.
So at HES, we have basically beam energies like we have here. And we have 80% polarization and don't need a figure 8. So why was there this field that you need this figure 8?
Figure 8 can preserve the spin in a way to cancel higher order, especially your precision go one way or the others. Let me finish. Okay. 12 GeV is not going to be there. It's different now.
Ah, okay, so it's much higher.
It's not much higher. Maybe you wait till I finish my talk, okay. You can ask questions. So this was 2013, it's been proposed. The hope was to not too much cost to add in. So at the beginning when they built, it can be approved at the same time to start constructing. But unfortunately, when they come down at that time in the 12th, 13th five-year plan, they approved a number of projects, and this is one of these. The final approved, they say, okay, your initial cost is this, now you increase a little bit too much, so you have to do it at the second stage. So that's why when 2015 finally it's approved, it was not there. And 2016 version, it's already changed. It's still 3/12. And now it's this year. So finally, it approved, the money comes down for the first phase. So since it's not, electron ring is not in the first phase, so electron had to come as second phase. So this is a version earlier this year, it was discussed. And this part is fixed, that's here. It's complete, design complete and going to construct. So now for the EIC, one part of this is try to also go above the epsilon threshold. So the first phase for EIC will be 20 GeV, and the electron is actually between 3 to 5 GeV. Could go all the way to 10, it's possible, but should to be 3.5, partly is also a possibility to combine with the E plus E minus machine, the super toy Chen factory, which is 3.5 is what they like. And the initial here is a warm magnet that it can reach 9 GeV. So before it can, this one, before it go to the EIC, we upgrade this to make it to be superconducting. It can reach up to, probably up to 30 GeV, but conservatively start with 20 GeV. So that's where the 20 GeV come from, which gave you the center of mass energy around 20, a little bit less than 20. So this can go from 20 up to 30. And
what is the difference between E ring and F ring?
The initial ring, I believe it's the warm one, and the upgrade one will be the forgot what's one of these will be superconducting. Just upgrade this to make it superconducting. They change the name for that.
It's in the same tunnel.
It's in the same tunnel.
And where is the collision point?
Collision point for EIC-1 will be here. And the initial design, they only put one detectors. So we had 2 meetings this year, and Abby was there for the second one in April. We had first one in January, and then the second one in April. April, there a few more people come, and I will mention that we'll have a next one next month. Okay, so this is where actually the site, how it looks like. This part is what the HIAF design is finished, design is finished, and now is construction start. And so we talk about first to have this part, and then the second EIC will be further away to add another figure 8. Okay, so the first version of this will just be an electron ring for 20 GeV. It will not be figure 8, but the longer one will be figure 8. So this one can go from 10 to 30 GeV. So here it's 25 GeV, although we put conservatively to start with 20 GeV. That's where it is. And the actually, the first one will be 3.5 to 5. We can go all the way to 10 GeV. That's initial design. And there's some parameters to show with 3.5 by 20, it can reach 1 times 10^33. Depends on how well they do with these focusings. Don't ask me about these numbers because I'm not familiar with how they do this. That's but some of you probably are expert in Accelerator, probably can check if this number makes sense or not. During the April meeting, we have both, I'll show you the names. May from, May used to be from Brookhaven, but she came to this meeting, and Yihong joined remotely. Yihong actually helped with, give them a lot of advice on some of these numbers, these properties.
So I can contribute 9 amps.
Yeah.
That's pushing anyone.
Yes.
You're right. Many of these numbers are pushing. You can.
I agree.
Okay. The main focus is on square root about 20, nucleon structure, nuclear physics, and get to the B meson productions. This is a slide from there. I want maybe show the next one be a little bit more the US part and the EIC in China. Kind of the lower part of this region. From Geneva, of course, luminosity much higher. It will be around 1033. Okay, kinematics, as I already showed there. So there were 3 working groups, one for accelerator, one for detectors. I'm helping them. Actually, I'm not really doing much. They are doing a lot of work. And then the physics, there are a few theorists mostly working on this to define the science case. So they try to have like monthly meeting, remote, and maybe every a few months have some video meeting. Then annually have some kind of meeting. At some point, we'll try to get more international involvement with this. So the goal is to produce some kind of white paper by end of next year. So some of the physics I was showing the US EIC, most of the C not gluon much. It's the spin and flavor, 3D structure can all be done, especially the light C productions like through pi and K productions, for TMDs, for GPDs also. And then pass through the epsilon threshold, can also study the pi and K structures. And it will not be able to do much with the saturation and others, even pattern variation, probably won't be able to do much. There also a great interest in China on the hadron spectroscopy. So they were very interested in once past the epsilon, they can also study 5 quark states. But there's no real simulation on that yet to see if luminosity is enough for that or not. So there are some simulation already done by people at IMP. This is the TMD projections for Collins asymmetry at the PT, different PT reading and the different X, different Z, and Q squared. So it can do 4 dimensions to pretty good precisions. This is for pions and also for cans. Cans precision a little bit worse, but still it's reasonable. And for DVCS, let's try to see if we can do this. One is single electron beam asymmetry, and also look at target transverse target single spin asymmetry. I think to compare with compass, because the energy range is similar, this target single spin asymmetry is really much advantageous, because when you need a fixed target, your dilution factor is a huge factor, a factor of 50 there. In addition to luminosity is about 1 order, but a factor of 50 makes 3 orders make it better than compass for the target spin asymmetry. Okay, so this is a few of the simulation. They try to do simulation on a number of the different physics topics, but it's still ongoing mostly. So we'll have next month, the third, yes, I almost finished. The third EIC discussion meeting will happen next month at Queensland Duke University. That's where Haiyan's place. So again, its topic is talk about science case, try to finalize what are the case we should do study. And of course, with the US study, many done, it's relatively easy to choose. And need to do the simulation for specific case. And also the machine design turned out to be much more challenging, especially try to push to the limit of luminosities. Okay, this is a timeline. And this is the 13th 5-year plan. 14 in China, it's every 5 years they have a long range the plan. And the reason this year this get a lot more traction is because they start prepare for the next, because 13th 5-year plan already finished, they start construction. They prepare for the 14th 5-year plan. And here is going to the 14th 5-year plan to finish. So the second phase cannot start in 14th 5-year plan, but you can ask for R&D money. So and then the construction will start in the 15th 5-year plan. And so early this year, the Academy of Science needed to gathering from nuclear physics, high energy physics, which are the major projects they want to do. So they put some material together and give to the state, whatever the commission in the state. So this already, I think they submitted in July. So they're waiting for what come out. If it's approved, they will get R&D money. They talk about 500 million Chinese yuan for R&D money, which is a little less, like a little bit less than 100 million, $80 million for R&D. And the construction, they talk about probably it's about $1 billion for constructions, for the phase 1. So I gave you a little bit of flavor of what solid project, and then tell you about what's going on with EIC in China. And of course, it's again, it's a beginning there. And after it was not in the first phase, and now finally start working on, it's being included as a second phase over here. The work is just starting this year, and it's slowly gain the tractions and getting more and more intensity. Hopefully, once it's reached some level, we can welcome all the international collaboration join. It will be nice facility complement to the US EIC and GeLab. Just the energy range is sitting just right in between these two. Okay, thank you.
All right, any questions?
No, go ahead.
Okay. So in this list of contact persons, I understood that was Zodang, right, on the theory side. So
It's
and then later you list the medium modification of the quantum distributions. He had the papers on the medium modified TMDs. Is that a part of the program?
oh yeah, yeah. For nuclei, he is a local one at IMP, but these two are kind of the conveners. One is Zhuta Liang from Shandong University,
Yeah, I know.
and GMP Ma from Institute of Theoretical Physics. He actually worked together with Yuan and Ji on the TMD factorization. I don't know that paper.
What I'm interested in is Zoltan's, whether there is a part of medium modified TMDs in the program. Because that is something that we don't have in our EIC program.
Right, right. Yeah, what's in the, I think Bowen and he also worked on this. They all both worked on that, yes.
And then one other comment I had was about your statement that in DVCS you have dilution factor of 50 making
Right.
difference. So if you
Compare with actually compare with the best, the simplest, just NH3 target. If you use others, even worse.
If you detect all particles, it is not factor of 50, it is just 6.
Yeah, of course, depends on your final state.
Probably you were talking about the error.
The errors, right?
The errors.
In terms of statistics.
It's not going to square because if you detect all 3 particles, it just 1/6 of the.
Yeah, you're right. Depends on the physics process. For inclusive, it's always just almost just that. But if a particular final state, there can be less. You're right.
Okay, did you have a question?
I have a lot of detailed questions on machine design, but we don't.
Machine side question. I won't answer you. Sorry. But I can get, if you have any question, I can send to Chen. He's the one. Yeah. Yeah.
Okay, one of your slides, you had something about saturation.
Saturation, I'm just saying this machine will not be able to do it. It's too low in energy. That's what I'm. That's the comment I just said with the physics. Yeah. I said this part, I just make it gray. Just says this machine won't be able to do the low energy. You need a high energy one. That's clear. Even that one we cannot do. Actually, we looked into that for the phase 2. It's already significant, but this with this low energy, these two physics goals we cannot do. This is what Harald is asking. We still should be able to do something, but we haven't done any study yet. Yeah.
Take this in the best spirit. I'm an outsider. I mean, if I look at this, I've seen this now for 6-7 years. It doesn't seem to converge. So, what is the planning if you don't hit arguments? I mean, just if I look at it, I still think it's a big mountain to climb here. To more or less get this. There's a lot of work still to go on the accelerator side. That's partly because you're moving. That's understandable. It still seems like a big mountain to climb. So, speculate a little bit about the planning and what happens if this R&D is not.
The former, first IMP itself already put a significant amount of money to do, just even finish the white paper, they already put some significant amount. But the process they're doing is for each, the first state, they come from academic science. Academic science is almost like DOE here, because all the institutions in all the research institutes belong to academic science, including IMP and IHAP. This is different from the academic science in US. Their academic science is real control of the money. So academic science already, they have a committee. They did this. The high energy part mostly come from IHAP. Already proposed to do the CEPC, also do R&D. Which the nuclear physics is this one. It's already in there and it's been moved up to the up level. So there's a very good chance it will pass through this time. Last time is initially The one is kind of approved here, but try to add this, squeeze it in, it gets into a lot of difficulties because the total money allocated is not enough. So this time for this, yeah, just earlier this year in January when I went for the other meeting, we had some discussion about this, and suddenly you need to move fast because Chinese Academy of Science, they need this. They say they need to find one project from nuclear physics to push up. And they look at several different ones and they choose this one. So it's already, it's a big step forward.
But now, by moving it, it's also much more expensive.
Right. And they wanted to go do something significant. So we try to pair them between the 12 GeV and the US EIC. This is a good window. So they say just whatever the cost you need and put it there.
How will you be able to estimate those kind of costs?
I didn't do it. It's they did it last time from the Accelerator side. They did it.
I mean, the question is that. I mean,
They did last time. They went through quite a bit of study when do the 3 by 12, so they have some experience. And even the rough private node, you home when they spend several weeks working with them. And they also have quite a bit of a collaboration IMP with GenLab on this coding experiment. So US side actually doing experiment there at IMP, use their ion machine. They have a coding sector. So some of this, not actually mostly not this year. Last a few years, there quite a bit of collaboration. From US side, it was initially encouraged for the EIC part of the collaboration. And it's in the US-China collaboration since 2010. It's one part of this joint GeV 12 solid is in there, and EIC collaboration is in there. It's continuous. So DOE is also, at least in the last few years, is encouraged in the EIC collaborations. So they did get a lot of support help from just discussion.
Yeah, but now you move, so now you need much more as Chinese to come with estimates for civil and just like that. So that's not
The civil part is actually that's the beauty of that is if you look at this, the central government approved this amount. The civil part mostly comes from local. Local government, they try to attract this facility there. The civil part they cover.
That's one thing is funny. The other thing is to make a machine and that's where, as we said, luminosity work.
Right.
Because you normally low energy machines have low luminosity because of the you cannot put so much space charge.
I understand. That's a part
so
of.
I think that is where my questions start. I can put these numbers on a paper, but how realistic is it to make that numbers work? Yeah,
the key problem is that
how big is your ring?
the size.
Size.
800 feet.
So that's the answer to your question on the space shuttle. So if you make it smaller, essentially, then you have less space shuttle from the lower end.
That's the other one.
This proton ray is 6
But
nanometers.
this is a synchrotron validation. I talk about the proton.
Yeah.
I think.
Now the cooling is needed. In January and in April, there was quite a bit of discussion about this, and it's clear it is still a challenge.
Space shuttle is okay. 600 feet to 25 CV, that's fine. That's you. Not a problem.
I'm glad to hear that. I don't know yet. I think they have this. I want to put this table there. They went through discussions. They felt this number. They're very confident, but to go to the red ones, is still some challenge. That's from just listen to their discussions. They're doing the cooling study, and they talk about collaborating with GeV, but maybe also collaborating with Rick. That's think Adi would suggest that part.
Well, maybe I was there. Right?
Maybe I was there,
She
yes.
was the one.
Yeah, she suggests some of that, yes.
I had a simple question. What is the motivation of having the proton in the electron ring different circumference?
Oh, it's the proton ring is kind of existing from here. The electron ring, you have to make it larger to avoid signature radiations. Just because the energy to allow between 3 to 5 GeV, you need enough size to avoid signature radiations. The larger the better in that way in terms of signature radiations.
And so
But
the
proton
3
ring
to
is
4
already existing, so we try to use existing.
I understand, but the ratio 3 to 4 is in some sense optimal.
No,
It's not optimal. If you want to save money, you don't change that. Then this one we cannot change.
I
And this
understand.
one is it's not necessarily optimal. It's just was.
So if you want to spy space charts, so if you have enough money, you always make the proton electron be completely separate. So essentially, to find space charts, you essentially just make the proton link small.
Small, yeah.
And more or less goes linear, more or less in energy and size of the ring. Which is partly why at Brookhaven and at GeV we start finding at the lower energy because our rings are too big for the lower energies. Essentially. For electrons, the other way around. You want to make it as big as
As
possible.
big as
So
possible.
why not make it 12?
For the electron, yeah.
Yeah.
You can make it bigger, yeah. And that would help you for higher energies later.
Right.
That's correct. Yeah.
So,
So electron, you want to always make bigger.
so what is the reason to take 8?
No, that's,
This
this is
They have available.
this is for this energy. If you want to high energy, you need to make it longer. That's this one. If we want to electrons ring start to be beginning larger, it will cost more money. That's
So the R&D for this has been approved and.
no. I'm saying the R&D for the maybe I didn't make it clear. The timeline is now the IMP putting some money to do the white paper, do all this study. That's just from Academy of Science give to them and they do it. But for this R&D, this they talk about 0.5 billion Chinese yuan to get from the state. So Academy of Science already pushed up, but haven't approved. This is a part of the 14th five-year plan. When they do that, they also look at 15th five-year plan. That's why they put this together. And even long term out there. But this is not approved. Should make it clear. That's the question Rolf is asking. If we don't have this, what will happen? I think there, if this is the project from nuclear physics push up, there's a good chance, but it's not approved.
Okay, any other questions? Comments? If not, let's thank the speaker again. So I think that ends the program for the day, unless there are some really urgent matters to discuss. Otherwise, on Tuesday in the late afternoon, we'll have a discussion.